Math, it's all about math, the wonderful world of math. Welcome to the wonderful world of math, astronomy edition. Today we're going to talk about polar coordinate expressions of conic sections, specifically regarding Kepler's laws of planetary motion. Rad, right? So Kepler had 3 laws of planetary motion. The first one that says a planet revolves around the sun in an elliptical orbit with the sun at one focus. So generally with an ellipse you have 2 foci. So the cool thing is that one of those foci is the sun, and the planet's path is an ellipse. Right? That's the first law of motion. The second one, the line joining the sun to a planet sweeps out equal areas in equal times. So imagine you've got a planet, and it goes from here to here in some amount of time. Now this line connecting the planet to the sun is going to be the same line connecting the planet to the sun later on in time. So if the planet's going this way in some amount of time, if I take this region of equal area and the planet goes this way, it's going to take the same amount of time to trace this area as this equal area. Same amount of time to go this little distance with this big long area as to go this longer distance with this bigger wider area. So that's the second law of motion. And the third law of planetary motion, the square of the period of revolution is proportional to the cube of the length of the major axis of the orbit. Remember, the major axis was the line segment with endpoints on the ellipse that passed through the 2 foci. It also ended up having endpoints that coincided with the vertices of the ellipse. Now, before we did this stuff in conic sections, the major axis was said to be 2a units long, and the semi-major axis, which is half of that, going from what we called the center to a vertex, was half of that, or a units long. So this would say the period of revolution squared is proportional to, means is a constant multiple of, the cube of the length of the major axis. So the major axis altogether, not the semi-major, but the whole major axis would be 2a cubed. That's the third law. Alright, so let's do something. In conic sections in polar form, we're used to writing this as r equals ed over 1 plus or minus e cosine theta, or the sine version, which is really not that different. But the thing is that d is not really useful for this astronomical type explanation or application. So what we're going to do is we're going to use something from the proof of the main theorem in this section, conic sections and polar coordinates. The way we showed that things of this form were going to be conic sections, and what kind of conic sections, from the proof of that theorem. And I know we're not doing that in this video. Go back and watch the bonus video where we prove the theorem. I'm just going to give you the relationship here from that proof. A, the length of the semi-major axis, is much more useful for these astronomical calculations, as you can see. So a squared, from the proof of that theorem, was equal to e squared d squared over 1 minus e squared parentheses squared. That's a squared. Now if we take this and solve for d, we can replace d in this equation or this equation with an expression in terms of a. So we're going to, first of all, multiply both sides by the reciprocal of e squared over all this other stuff that we don't want with d, and leaving us with this. And then the next thing we're going to do is we're going to take the square root of both sides. The square root of d squared is going to be d. Normally you say plus or minus, except that d is supposed to be positive. A is supposed to be positive. Because we're talking about ellipses here, we want e to be less than 1. So 1 minus e squared is also positive. And of course e, always positive. So you're looking at this for D. Well, now we can take that and plug that into our equation. If we have one focus at the sun at the origin or pole, let's go ahead and stick to r equals ed over 1 plus e cosine theta for now. What we've learned then is that this becomes r equals e times a 1 minus e squared over e over 1 plus e cosine theta. Now you see this e and this e, they cancel, leaving you with r equals a times 1 minus e squared over 1 plus e cosine theta. We've eliminated d, which is not helpful for finding equations or tracking the ellipse through space. And this, the way we've chosen it, is going to have directrix x equals, instead of d, we've gotten rid of d, but we're going to use something that's equal to d. The next part is some vocabulary words that are kind of fun, with some pictures that are also kind of fun. The position of a planet closest to our sun is called the perihelion. So you've got the focus, right, that has the sun on it, and then it's got a vertex next to it, and the closest vertex is called perihelion. But you've got another vertex, right, and this one is going to be actually as far away as the planet can get. This is going to be called the aphelion. So you've got perihelion, the closest position, and aphelion, the absolute furthest position from the sun. That's for the sun. Now if you're talking about the Earth and the moon, you have slightly different words. The closest position is called the perigee, and the furthest position is called the apogee. Now that's specifically for the Earth. This g that makes perigee is the same g that makes geometry, the measure of Earth, and geology, the study of Earth. But wait, it gets better. I've got two more of these things. For Jupiter, because Jupiter has 79 moons that we know of at this point. This happens a lot. The position of a moon of Jupiter closest to the planet is called perigove. Ha! And the position of the moon of Jupiter furthest from Jupiter is the apogee. Right? Rad. And then we've got kind of the generic term. If you have the position of a moon of something, like say Saturn, or Mars, or Neptune, or Uranus, or other stuff way out there in the solar systems that we don't even know that well. The position closest is called periapsis, and the position furthest is called apoapsis, which is a fun, weird word to say. So the example we want to do first is, suppose we have Titan, a moon of Saturn, in an elliptical orbit around Saturn. We want to find a polar equation for this orbit if we're told that the length of the major axis being the entire thing here, is 2443740 kilometers. So that's 2,443,740 kilometers. And if we're also told the eccentricity. Once we've got our equation, we're asked to find the apoapsis and the periapsis distances. So the polar equation, r equals a times 1 minus e squared over 1 plus e cosine theta. The major axis from here to here we said was 2a. So if we want a, all we have to do is divide the length of the major axis by 2. We're given e, so we just need to plug it in. If this is 2a, then a divided by 2, 1,221,870 kilometers. So r is going to be all of that times 1 minus 0.0288 squared over 1 plus 0.0288 cosine theta. Simplify at least the numerator for me. Square e and then subtract it from 1 and multiply by a. Alright, ready to check your work? We should get 1186680.14 over, and we can't really do anything about the bottom. There's nothing to simplify down here. So that's what we get. Now this is the equation that we were asked for the elliptical orbit. We were also asked for the apoapsis and the periapsis. Now look at the picture, right? If you've got this, and you've got the periapsis, this occurs for a specific theta value, right? When theta is 0. And the apoapsis occurs for when theta equals, that's right, pi. So all we have to do to find the periapsis and apoapsis distances is use theta equals 0 and theta equals pi. I realize, of course, that I drew my picture up here wrong. I put the Saturn, at the wrong focus. I have a tendency to do that. Sorry. This is the one that's going to have plus on the bottom. Not that it matters, but this is the formula we use. This picture is going to make sure that periapsis is when theta equals 0, and apoapsis is over here when theta equals pi. Well, when theta equals pi, cosine of pi is -1. So what you're looking at is r equals 1186680.14 over 1 minus the eccentricity. And this is 122.1869.996 approximately, right? It's not equal. You're dividing by some really kind of longer decimal than you'd like to divide by. But because A was in kilometers, this is in kilometers. And of course, if you round this to the nearest kilometer, that's going to be a pretty big number. Now for the periapsis distance. Periapsis distance is going to be when theta equals 0. Now cosine of 0 is +1. So it's going to be very similar to what we just had, except instead of minus in the bottom, it's going to say plus. And this is approximately 1153460.478 km, or rounded to the nearest kilometer. Oop, I forgot the 6. There we go. And you'll see that the apoapsis distance is greater than the periapsis distance. And there you go. Those are the 3 things we were asked for this problem. So let's try another one where I give you different starting information and ask similar questions. Find an equation in polar coordinates for the elliptical orbit of Jupiter's moon, Europa, if Europa has an orbit with an eccentricity of 0.009. If it has an apogee distance given here, and a perigee distance given here, and we're told that the focus is at the origin, and once again I put the wrong focus in the middle. There we go. Okay, Europa. Now Europa was the mother of King Minos of Crete. You guys probably have heard of the Minotaur, right? Half person, half bull. Well, that wasn't actually King Minos' son. It was his wife's son. But that's all besides the point. What is the point? The point is, in order to come up with the equation, we need the eccentricity, which we were given, and we need A, the length of the semi-major axis, right? It usually helps to have the length of the whole major axis. So let's look at what else we were given. The apogee distance. apogee distance is the distance from here to here. The perigee distance is the distance from here to here. Now, what do you get when you put those together? Apogee distance plus perigee distance adds up to the entire major axis. So let's go ahead and add those things. This tells us then that 2a is going to be 1341800, or 1,341,800. So to get a, we once again just divide by 2. 670,900. This is the length of the semi-major axis, and this is one of the critical components of our equation. R equals A, all this business, times 1 minus e squared over 1 plus e cosine theta. Again, I'd like you to simplify the numerator at least. Square e, subtract it from 1, and then multiply. And when we check our work, we should get 664,861.9 over 1 plus 0.009 cosine theta. We can actually write this without decimals if we multiply the top and the bottom by 1,000. That's the number of decimal places, maximum number of decimal places. And it looks like this, which is slightly better. You look at our question and we find out that that was all we were asked for, was this equation. Now, in general, we can examine the perihelion distance. We know that it's going to be when theta equals 0. So if we have the generic equation, right, we can just plug 0 into that. 1 plus e times cosine of 0 would be just 1 plus e, right? And this factors. This is actually a difference of squares. 1 minus e squared factors as 1 minus e times 1 plus e. So you see there's a common factor of 1 plus e at perihelion. So this is the perihelion distance every time. And for aphelion, you're going to get very similar stuff. Theta is going to be pi, and you plug this in. R equals a times 1 minus e squared over 1 plus e times cosine of pi. Cosine of pi, though, is -1. So instead of saying 1 plus e times -1, we just say 1 minus e. But this thing factors just the same way as it did before. It's still a difference of squares, only now there's a different common factor from top to bottom. So you're going to be left with a times 1 plus e. And that's your aphelion distance. Okay? And that's all we're going to do for now with Kepler's laws. You can do more later with more calculus. So we'll see you next time. Our word of the day is apsides. Periapsis and apoapsis together are pluralized as apsides. Cool. This has been a Badger Bear production. We'll see you next time. Party on, dudes.